I think.
Now we're live.
Yeah. There you go.
So for those of you just joining in, James and I have covered the background of what Phong shading is, the Foley and Van Dam book, specular versus diffuse shading, and we did it all for nothing, and we're not going to do it again. So,
one more time. Quick feeling.
I'm just going to do this. This book is called the Foley and Van Dam book, Foley, Van Dam, Computer Graphics, Principles and Practice, and you can look up Phong, there's Phong shading, Phong, and illumination, Phong in the index. You want illumination, Phong, and that will give you the list of, or that will give you the pages to refer to. It's in the 700s somewhere of how Phong shading works. So, how do I turn this into screen sharing? I don't want to turn my camera off. What I do want to do is create a folder called UTB, which stands for Under the Bed, and grab everything on my desktop and drag it in there. I don't have anything on my desktop that I'm embarrassed about, but
not today, anyway.
Anyway, yeah, exactly. Okay, so settings. Nope, that's okay. And come on, there's got to be a share screen. I see capture, Q&A.
Screen share is the green-looking button that says screen share if you hover over it.
And that's going to share my entire desktop, both windows. Oh, and I've got the infinite tunnel of James now. That's awesome.
Yay! I see you seeing me.
This is very meta. And it's appropriate to a discussion about ray tracers, isn't it?
Right, yeah, exactly.
Okay, so what I'm going to have to do for my own sanity is minimize. No, that's the wrong minimize button. I'm going to minimize Hangouts. So are you seeing both desktops?
No, just one. It should have asked you which one you want to show. Did it not pop up a thing to say which one you want to show?
No, it just.
I'm seeing your terminal now.
You're seeing the terminal. Okay, and then just to confirm, now the terminal is off the screen?
Nope, still on the screen.
Okay,
yes, yes, it went away. It went away.
Oh, it did go away. Okay, cool.
It just lagged.
Okay. Alrighty then, let's go ahead and expand this guy, clear that guy out, and what we will do is create a directory here called Fongy. So, boy, what's going to be the easiest way to do this? I think what I need to do is I need to pull up my own tweet. Don't copy my password. Everybody can see that it's a bunch of dots.
Just taking a few screenshots, no big deal.
Yep, yep. This is going to YouTube, and the careful viewer now can actually capture the email I used to register with Hootsuite. That's awesome. All right, so I don't want to look at that. Actually, you know what? I'm going to put Twitter and all my private messages on the monitor that you can still see. Crap. I'm going to hide direct messages. How about that? Man, I hope Google lets me edit this video before it goes live.
You can edit it. You don't get to edit it before it goes live. It just goes live. And their editing is kind of simplistic, to put it nicely.
Yeah. Okay, so here's this awful mess. Joe Grossberg chastised me for, he says, you know, not to be a wet blanket, but it's kind of poor form encouraging people to run obfuscated code. and I countered with at least my code is honest. I mean, if you see that in a tweet, you know what you're getting into when you try to run that. I feel a little more frustrated with people who say, "Oh, you can install RVM by just doing curl random URL and piping it
curl
to
some URL on the internet. I'm sure that's fine."
Yep.
And feed it to a shell, and maybe sudo while you're at it.
Yep. Yeah, exactly. So okay, so here's this Phong shaded ray tracer kind of in a tweet, and
that's awesome.
Well, I'm gonna screw this up, but I'm gonna do my best. So I don't even know if we need to create I mean, it'd probably be cool if we wrote a program and then ran it, but what for right now? So let's for now let's just get a sphere up on the screen. This is actually really easy to do. The part in the tweet that is really important is this -1 step to 1 in increments of 0.03. Okay, and what this is going to do is it's going to move from -1 to +1 in 0.03 increments. And guess what? Our sphere is going to be centered at the origin, and it's going to have a radius of 1. And so if we change the step that it's being rendered in, it actually changes the size on the screen that we see the sphere. So that's the y-axis. If we do -1 step 1, and by the way, I found out through experimentation that obviously there's another way to do this, which is to like to generate a range and step over it and then scale it down. But when you're trying to fit into a tweet, using integer step, other integer, and then a step value, much smaller in terms of cryptic code and fitting it into small values. So what I'm going to do is I'm going to say, so the formula for a sphere is x squared plus y squared plus z squared equals some constant, right? That equals the radius squared of the cube. And guess what? We're using 1 as the radius. There's I want to say it's our first shortcut, but it's about the 15th really. But yeah, we're going to use basically we're going to say at each value x and y, we're going to say if x plus x plus y is less than 1. Now this is actually the formula for a circle, and we could do y 1 times 1, but you see how that collapses, and so that's why using 1 as a radius is a value. If we're inside this, then we want to print a hash mark, and if we're not, we want to print a space, and that scans. That's the inner step, which scans left to right across the text screen. Once we get to the end, we have to do a put statement to put the new line on and do the next y. And that right there actually should be enough to give us a very badly squished ellipse. That's a surprising result to me. Oh, I see why. 0.015. Okay. Now, here's a pop quiz for you, James. When I'm stepping in the y-axis, I step by 0.03, but when I step in the x-axis, I step by 0.015. 3 guesses as to why, and the first 2 don't count.
Okay, so hang on. Let me go through this and make sure I've got it so far.
Okay.
Okay, so what we're doing is we're moving from -1 to 1. I get that. That's our drawing space.
Yep.
So we'll do 2D for the sake of my brain.
Yep.
Where 0, 0 is dead center in the sphere, and
Yep.
going up is to positive y, and going down is to negative y, and then left is negative x, and right is positive x. So I get that.
Okay.
And then you stepped over those points, and let me make sure I understand the stepping. So the stepping would be effectively the resolution of our image.
That's exactly right.
Okay, so the stepping is the resolution of our image and how many increments we're going to check. And then what you did is just inside the loop, you use the equation of a circle to tell if that point falls inside or outside of the circle.
That's exactly right.
Okay, all right, I have it. So the reason you had to use a different resolution on one, and the other is the fact that, let's see, 0.3. Nope, I don't know. Why?
Aspect ratio.
Aspect ratio. Okay, walk me through that.
Okay, so the short version is that if we go, let's see, V-E puts, so we're stepping across a total of 2. If we divide that by 0.03, we have 66, 67 lines vertically to play with. But in order to make this thing circular, in the X dimension, we actually have to print out about 133 characters. If I were to step by 0.03, this would be, if I had a perfectly square display, I would now, you can now see that we're dividing by 0.03, and 0.03 is our step now.
Right.
So this image is going to be 66 by 66 pixels, and it's not circular because a character on a text display is about twice as high as it is wide.
Ah, gotcha.
So this is not just shortcuts, this is brutal hacks and kludges.
Yeah, no, it's kind of neat though, because yeah, like I get it.
Yeah.
So it's because yeah, but if you were printing to let's pretend we weren't doing a terminal. Let's pretend we're doing pixels in an image or something. In that case, you could use the same step, right?
You can, as long as the pixels that you're using are in fact actually square.
Right, and so you would need, like, if you're going to draw this in an image, you need to make it like 400 pixels by 400 pixels or something.
Right. Unless your monitor isn't quite square, and I don't know what the standard for hardware is anymore, but when you and I were playing around with Raytracers and Pavre, right? We had like VGA mode, and it was like 640 by 480, and the monitor was really close to square. I mean, it wasn't square, but it wasn't the same ratio as 640 by 480, right? There was a little bit of skew. I want to say like 10 or 15% skew. I could be totally making that up. I don't know.
Right.
But we would throw in this aspect ratio to make circular things look circular.
Right.
It reminds me. This reminds me of watching a Western on TV when we were kids.
Right. Yeah.
Right? When they get to they do the whole movie and they've just chopped it to fit on your TV screen.
Yeah.
But the credits are too big to fit, so they squish the aspect ratio, and all of a sudden everybody is 7 feet or 17 feet tall.
Right.
So yeah, aspect ratio is.
That's cool.
Is kind of our friend here.
So then if you just, for fun, if you wanted to draw a different shape, like a cone or whatever, you just replace the function in the middle with whatever the function of a cone.
That's exactly right. Yeah, right here I'm using, x squared plus y squared is less than the radius squared of my circle.
Right.
And yeah, the cool thing is I can actually change that radius, and now we get a smaller circle and whatnot. But yeah, if we change the formula, like if I do x, so I've got x squared and I've got y squared here. You know what? For readability, I'm going to go ahead and square these. So that should be the same image. Yep. Okay. So I've got x squared plus y squared, and yeah, this is actually the formula for any ellipse, right? If I do 0.9 times y, you can see that the circle is now starting to stretch off the top and the bottom. It's actually kind of hard to see. Let me go the other direction. I'll do 1.5 times y. Now we get an ellipse that's kind of flattened out, and I could, in theory, I could rotate that ellipse, but that gets a lot harder because now the foci of the ellipse aren't axis aligned, and I'm not going to play with that.
Right.
But yeah, I mean, we can do the same thing, right? We can make the ellipse, thinner instead of taller, or taller instead of wider, by fiddling with X. So yeah, that's literally what this is. I guess you would call this hit detection in Raytracer. we're basically saying, does the ray we are casting out fall inside the sphere that we are rendering? And so that is kind of step one, is to get, if we were just, if we had no illumination other than like we were taking an X-ray of the photo, here we have a clear X-ray of our sphere, right?
That's awesome.
So now we get into, I'm looking over here on the right-hand side. I'm looking at the other garbage that I put in here, and boy, there's just so much of it. Let's see. So now we get into like height detection, like how tall is our sphere here, and I'm going to go ahead and I'm going to talk about color quantization next. So I think what I want to do is right here, instead of printing a hash mark, what I want to do is I want to print out from 0 to 9 how tall the sphere is. Does that make sense?
Okay.
So that's going to be, oh boy, what is the formula for z at this point? Z is going to be, okay, if x squared plus y squared plus z squared equals 1, I'm trying to do this in my head, z squared equals x squared plus y squared minus 1 squared, and therefore z equals the square root of x squared plus y squared minus 1. So that's going to be a mess. But what we're going to do is we're going to say 9 times 9.99. If I do 10, there's a small chance that I'll get a 2-digit integer right at the center of the image. And then we're going to round that down to an integer. And if I print that, we're going to crash. Numerical argument is out of domain. Why is that the case? You know what, I'm just going to get rid of the 1. That's probably a bad idea. Yeah, that was a bad idea. This is the fun bit when you're like screwing around and like things just stop working the way you expect them to. Okay, so it is possible for x squared and y squared to be less than r squared. So what is... People out there who do math are watching me right now going, Dave, you idiot. So obvious.
So in here, x squared and y squared have to be... No, it's not possible for them to be bigger than r squared. Is it? Not in this parenthesis. Because didn't the conditional check for that? So what?
Oh, it's actually the opposite way around. They can't, so x squared plus y squared together are less than 1. So if I subtract 1 from this, it is guaranteed to be a negative number, which means it's the exact opposite. I can't subtract 1 from this and get a valid square root without using imaginary numbers. So it doesn't like that. But then again, why doesn't this work? Why is that printing zeros everywhere? Let me take out the dot to make sure I'm not getting decimals.
Oh yeah, good point.
I am getting decimals.
Okay. Because order of operations, you're doing 2i, and then you're multiplying it by...
Yes. There we go. There we go. Okay. So that's kind of pretty looking.
That's kind of cool, actually.
So it's interesting to note that we have 9s. Yeah. So it's interesting to note that we have 9s out at the edges and we have 0s at the center. And the reason for this is basically this is... how to put this? this is the number that you're looking at is basically how much of this pixel is made up of X and Y component, and how much is left over for Z. So out at the end, 90% of it is made up of X and Y. Less than 10% of this vector of its three-dimensional space is left up in Z, is left up to the Z axis. Right in the center, we have zeros, which means that this vector is, baby, it's all Z, right? There's very little X and Y going on. Everything's happening in Z. So you can kind of envision that as if you draw a vector from the center to the edge of this sphere, it's going to be 1 unit long, no matter what. That's another shortcut that I very deliberately picked, especially when we start getting into the trigonometry. So what's going to happen is, as this vector moves anywhere on the screen, it's going to have an X component, a Y component, and a Z component. And the closer we get to the center of the circle, that vector, it's going to be, you know, it's going to be like 0.001, 0.001, you know, 0.912, you know, 918, something like that. It's all Z component at the center of the circle.
Right.
So this is a little bit counterintuitive to what we were thinking. I was thinking I was going to build this height map, and I was going to show us, you know, how tall is the sphere at any given point. And I can do that, but to do it, what I need to do is I need to say 9 minus. Actually, I'm going to say 10. Is that going to be dumb? No, I can't do 10 minus because I've got zeros in the center. I'm going to say 9 minus that number. And now we have the same sphere. And now it's a height map, right? I mean, the sphere is very flat, or very close to, or I guess very close to the, what would you call it? The XY plane at the edges, and at the center it's very tall.
Right.
And we have these nice, almost concentric-looking rings. Well, sorry, they are concentric-looking rings, David. Figure it out. But what we also have here is the thickness of the bands looks about the same, which is not exactly what we would expect with a sphere, right? I would kind of expect something a little bit bigger. You know, I would expect the 9s in the center to be a little bit bigger, and the zeros on the side to be, you know, considerably thinner. And there's a reason for it, and the reason is math, and I don't know that I can explain it well, other than the fact that we are not considering r squared. We're considering r as a flat vector. We're not considering r in a two-dimensional space, and I could be wrong about that. But so I've got this 9 minus 999 thing. If we look over here in my tweet, you can see in this, I don't know if you can see me highlighting this tweet, but you can see...
I can't see your tweet.
I can't see the tweet, okay.
Nope.
Let me bring the tweet over here. So this highlighted section of the tweet has this 1 minus x times x minus y times y.
Right.
That's the height, that is the z-axis. That is the height of the z-axis at that point in the image. That is exactly what is going on there.
Okay.
And I wanted, you can see that there's no math dot square root in here because I'm being just a gross hack at that point. Actually, I wonder what we can get. What will happen if we take away that square root? We know that x squared and y squared are less than 1. Again, not what I expected.
It's cool, though.
Oh, it's because I'm multiplying x and adding y to it, or again, order of operations. There we go. That looks like a sphere. We got this nice big flat area across the center of the sphere, and then as we get to the edges, the bands get thinner and thinner and thinner, and that's because the walls of the sphere are sloping away from us.
Right.
Does that make sense?
Yes.
Okay. So again, we are cheap tricking this like crazy. But at this point, I've got this nice little 9 to 0 printing out here. Let's go ahead and add color quantization, and this is if you were using Pavre back when you had like 256 colors, right?
No, after that.
Oh, okay. All right.
I bet it was cool then, though.
Well, it was about as cool as the crap we have on the screen right now. You have what's called color banding.
Right.
Come as a result. GIF images to this day are limited to 256 colors, and so when you want to render a GIF image, you have to quantize your color space. You have to take all the colors in the image and reduce them to 256 colors. And sometimes when you get a smoothly shaded object, you really need, 10,000 shades for this to look natural.
Right.
And you don't have that. You have 16 shades of red available to work with, and so you're going to end up with this banding color.
Right.
And so let's use this tweet. That is actually what this C equals this garbage here, and the 4 times and the +4, that is my color quantization. This is 8 characters long. That is the color at this pixel. And at the time I wrote this tweet, I basically went through a whole bunch of images and just compared if I have a solid wall of periods versus a solid wall of commas, which one is brighter? And the answer was commas are just a little bit brighter than periods, and lowercase o's are just a little bit brighter than that, and hashes, surprisingly, are not very bright. Ampersands, capital O's, might be zeros. Actually, I think it is zeros because they have the line through them, or they have the dot in the center of them. And then, surprisingly, most of all to me, percent signs were the brightest image in that font. When you use them as shading, ASCII art shading characters, this is basically a dark to light color band.
Gotcha.
Okay, and it's 8 characters long, and our x squared plus y squared, the step that we're moving from is moving from -1 to +1. So we multiply it by 4, which now gives us. This is 8 characters long. We now have a number between -4 and +4. So we add 4 to make it go from 0 to +8, or in this case 0 to +7. So let's add color banding to this and see if we can turn it into. I mean, right now we're looking at a mathematical representation. Let's see if we can make it look pretty. And so I'm just going to copy the color banding stuff that I did here. Oh, I have to split it because I need it to be an array. And then what I'm going to do here, instead of this 9 minus 9 times 999, I'm going to get rid of all of that. And I'm going to say I'm going to multiply this whole mess by 4. I'm going to add 4. I'm not sure, but I think I have to 2i this. Boy, I've almost got Lisp here. I've got enough parentheses. And then we're going to use that as an index into the C array. Let's see if this works. Nope. Unexpected token.
Uh-oh.
Oh, it's because.
It is
yeah,
less.
single quote versus double quote.
Nice.
Oh, okay, so it worked, but it worked in a really weird way. This does not match my expectation of the color banding. Oh, I've lost my 1 minus out of here. So if I put that back in, I have no idea why it has done that. But that is
That's
cool.
amazing. You turned that sphere into a piece of pie.
I did. Who wants pie? That is so cool looking. This is ridiculous. What on earth have I done?
And this is exactly what it was like to play with ray tracers back in the day, by the way. You would make some adjustment, render the picture, and you would be like, what is that?
Yeah, I've turned my teapot into, the Tower of Art from Ultimate Pork. It's this weird 7-dimensional tesseract. Boy, I am just. You can tell that I did not have time to prepare you a clean set of steps to walk through here. Okay, I do know that I've got. I'm going to start stealing from what I've written over here. I really do have 1 minus x squared. Oh, minus y squared. Or I could put the x and y in parens. That would work. Okay, and that's unnecessary parens because order of operations. Okay. Now the interesting thing here is that this thing is brightly shaded at percent, and it shades down to the hash symbol, and it doesn't shade any less.
It looks like it's only using about half the shading.
It is. In fact, that's exactly the case. And the reason it's using half the shading is because the half of the sphere that is behind the plane of viewing,
right?
That is using the other half of the color palette, but we can't see it because it's on the back face of the sphere.
Sphere, yeah.
Okay. Now, in order to move the camera, we're going to be okay with this. We're going to leave this here, and the reason why is I'm about to turn our light source so that we can actually see parts of the sphere that are not lit from the front at all. Now, in a perfect dark room, these shades would be black, right? Because it's like the dark side of the moon, basically. But because we're doing hacky approximations here, you can basically assume the cracks in the math is where this model has some illumination on it from all angles. And so that is actually what's going to happen. Now, I talked earlier about Phong shading, and Phong shading is this, and we're actually starting to approximate it here. We've got basically our own eyeball is the light source. This is a view of the moon from the sun, and it's perfectly shaded out as a sphere. And I'm going to start kludging the math a little bit, and that's going to cause some leakage in the light model, which is actually going to turn out to be cool, and we're going to be able to use it. So basically, we're going to accidentally illuminate this model a little bit from within so that we can actually see the dark side of the moon. But in order to see the dark side of the moon, we need to move either the eyeball or the light source to not be coincidental. We need to not be lighting this thing from our own face. And what Phong shading does is it basically says, well, and it was that formula that I put up on the screen, before we started broadcasting. Phong shading basically says we take the illumination vector, we take wherever it hits on the model, whatever pixel we hit, we have to figure out what the normal vector at that point is. We rotate the illumination vector around it, and then there's some angle alpha that is our viewing angle is not quite at that reflection spot.
Right.
And what Phong does is he adds this exponential term to alpha. And the higher the exponent that he adds on this alpha, the brighter the shiny spot on the illuminated model becomes. And the rest of the rest of the illumination becomes diffuse lighting or non-Phong shading. And what I'm going to do is I'm actually going to turn this model, and at this point, if we were doing a proper lesson on Phong shading, what I should walk you through is matrix rotation of a vector, and what we're going to do is we're going to have an incidental light vector, and what I'm going to do is I'm going to hand wave all of that away and basically say, no, if we just assume that the illumination is coming from some vector over here, and I'm literally going to make up a vector here. Let's see. And I have to get my pluses correct here. What I'm literally going to do is I'm going to shift, take our axis, I'm going to multiply the x-axis by 0.3, I'm going to multiply the y-axis by 0.6, and then I'm going to take this whole mess that we've got running right now and multiply it by 0.6. So that's basically, this has become our z-axis. And I have to get rid of the 4 times. So this is now our z-axis, this 1 minus x squared plus, well, actually, that is our z-axis, 1 minus x squared plus minus y squared. That is our z-axis. So if I multiply the z-axis by 0.6, the y-axis by 0.6, and the x-axis by 0.3, it's going to effectively turn the light source away from, it should, if I've done this correctly, x is going down, y is going across to the right. So I've multiplied x by 0.3, so it's going to move the light source a little bit to the right. Y is multiplied by 0.6, so it's going to move the light source quite a bit down. And then the z-axis is 0.6, which means it's going to move the light source quite a bit towards us, into, out from the monitor in z space. And I have to make sure I've got my parens lined up. I'm sure I don't. But what I can do is I can say 0.6 times this mess. So there is our entire, nope. Okay. So if I dump that, that's going to give me math. So this is now going to yield a number between -1 and +1 that is basically the illumination vector rotated. The reason I chose 0.3, 0.6, and 0.6 is because these are pretty close approximations to what a unit vector is. Right, you remember like we have magic triangles like 3 and 4. If those are the sides of a right triangle, you know that the hypotenuse is 5.
Okay.
Right, because 3 squared plus 4 squared equals 25. Square root of that is 5, right? This is the Pythagorean theorem. This is the Pythagorean theorem in three-dimensional space. If you have, a 0.3, 0.6, and 0.6, and you square those and add them together, you get a number that's pretty close to 1.0. So it's the three-dimensional Pythagorean theorem. So now I need to index into this bad boy. And in order to index, I've got to play that game where I multiply it by 4, and then I add 4 at the end. And now in my tweet, I don't actually do the 2i thing, so I want to check something really quick. Puts, let's see. If I take 1 to 10, make that an array, and then say, give me element 3.4, it prints out element 4. Okay, so I don't have to 2i this. That's awesome. That's why it's missing from my tweet. So this might actually work. I have basically...
What the hell did Ruby do there? So, element, because it's over 3...
Huh? Yep, it gave me element 4. It rounded up.
Wow.
So,
That's
or no,
cool.
it gave me... Let's see.
No, it gave you the 4, which is at position 3. It truncated it.
Let's see. This is not a zero-based array. So.
Oh, it's a 1-based array. Yeah.
Yeah, it is actually position 4.
Yeah.
So.
Yeah. Wow.
There we go. So this mess is very close to the thing that I put in the tweet, and that 0.3x or 0.3 times x plus 0.6 times y plus 0.6 times the formula that we've been working on, which is that 1 minus x squared minus y squared, that actually gives us an angle of rotation. And it gives us, I am totally cheating the alpha vector, which is the difference between the reflection vector and the viewer angle, I'm cheating all of that away. And you can see very clearly in the text now, we have the lowercase o, we have the commas, we have the dots. We can now see the dark side of the moon. We can see the sides or the parts of the sphere that were behind the XY plane when we were viewing directly from the point of the light source. Does that make sense?
Right.
So I just realized this was really cool, and then there was a really hard step, and then it got really boring, because basically what I have done is I have collapsed all of the trigonometry from Phong shading and just made it go away. And I have collapsed the exponent in Phong shading. So actually, you could almost make an argument that it's unfair to call this a Phong shader, because it's sort of like saying a circle is a sphere if the z-axis has been flattened to 0. Right? I've eliminated the exponent of the Phong shading. So basically, what we have here is actually diffuse illumination, but it is point light source. And we could throw in all of the mess to figure out, Phong's illumination model, but yeah, I dropped the exponent on his element to 0 so that all of the specular reflection becomes 1,
Right.
or 0 in this case, or well, it becomes a multiply by 1, and so this is what you end up with in the final tweet. That is, and I think the code that I've written here still does fit in a tweet, but yeah, what you've got here is a Phong shaded sphere ray traced at a bash prompt in Ruby, and that's it. Now, what might be fun would be, and we talked about this on Ruby Rogues yesterday, or a couple days ago. Of course, this video and that podcast are going to be cast adrift in time, so we talked about we just recorded the Why Ruby Sucks video, and we talked about how there's really poor graphics support in Ruby. And if we wanted to do something cool with this going forward, I would probably want to open up RMagic or Gosu or some other one of the windowing toolkits, and I would want to play games like put up a background image and then actually render a high-resolution sphere with this lighting model. And I would actually write a vector class. Actually, Ruby's, I think, does Ruby have a vector class?
There might be one in the matrix library. I can't remember.
But I would actually do like angular rotation. I would invert the normal vertex, and I'd throw in. At this point we're talking about a 100-line, 200-line script. But that that 100 lines buys you some things, right? I can do a diffuse lighting model and a Phong shaded lighting model. I can add a specular component and a diffuse component to this guy, and shade it in various ways, and then render it over a background. And so you could have this, this red, racquetball floating in space with light shining off of it, and you could put whatever back. You could put, a space background on it or whatever, and now you've got this ball floating in outer space, and that's basically how to write a Raytracer in under 140 characters.
That's pretty cool. It's interesting that when I play with graphic stuff like this, I often use the PPM image format. Are you familiar with that one?
Vaguely.
So PPM is like the world's simplest image format.
Okay.
It's totally straight ASCII. Well, it can be. It has a binary format too, which is faster, of course, but totally straight ASCII and stuff. And then what's awesome is you can get a command line tool. If you install NetPBM, you can get a command line tool that's basically PPM to JPEG. Is exactly what it is. So then you can write out this stupid, simple ASCII format and then just pipe it through that, and you can end up with a JPEG image. I'll send you a link. I'll give you a link here in the chat room. But that's my favorite way to play with simple images like this, because I can write it really simple image-wise and get actual image output.
That's cool.
Yeah,
Very
it's really easy. It's the world's easiest image format. Everybody should know it because, like, it's so stupid simple.
yeah.
And then you can just pipe it through. Like I say, if you install NetPDM, which you'll see on that link if
Yeah.
you go to the one, but if you install that, you get a PPM to JPG, and then you can just pipe it through there and get a real image.
Is it PPM Papa Papa Mary or PDM Papa David Mary?
It is the image format I just described is PPM. It's Papa Papa Mary, and then but it's part of the Net PBM package. Papa Baby Mary, and that package has several image formats in it, but. PPM is the one that I think everybody should know because it's so stupid simple.
Yeah.
And you can just give, like, red, green, blue values. And,
Yeah.
so
yeah. The funny crazy thing is that oh gosh, back in 2000, it was 2002 because it was when the Olympics were here in Salt Lake, and my office was about 200 yards from Rice Stadium, and they, the Secret Service evacuated us. They basically said, you can't come to work here. Oh, and by the way, we need the keys to your rooftop. And, and we're like, are you gonna put snipers on our roof? And they said, just give us the keys to your rooftop.
That's awesome.
And go home, and don't try to come to work during the Olympics, because we will know that everyone has been sent home. So anybody trying to get into these buildings is going to be met with extreme suspicion. And so yeah, we all got a 2-week vacation during the Olympics. But I ended up writing. I was writing a graphics driver. We had the NVIDIA GeForce had just come out. We were just starting to do 3D acceleration down in the hardware. They'd been out for a couple of years now. Second gen GeForce cards were coming out, and I was working on a graphics card at Evans and Sutherland called the Real Image, and the Real Image 4K, and this is back in the day when, if you had 2 gigabytes of memory in your machine, you had a ton of memory, and you didn't have a pair of 2 gig sticks, right? You had 8 slots, and they were each filled with like 128 mega or 256 megabytes. That was the biggest DIMM you could get back then. This was the time that Dr. Howard. Era T. Howard.
Oh yeah.
This is the time when he was doing research on Katrina.
Right, for NOAA. Yeah.
Yeah, and he posted to the list that he had a machine with 8 gigabytes of memory in it.
Right.
And I went back and calculated the cost of memory, and yeah, he had like $4,000 to $6,000 worth of RAM in his machine.
That's awesome.
Back then, and that was prices back then, so in today's dollars it's 50 bajillion. But anyway, this is a long rambly story, but the point of it is that I frequently needed to generate reference images, and I was tired of just saying, here's a triangle, shade it this way. And so I ended up writing, I was doing Perl back then. I hadn't discovered Python, and from there discovered Ruby, so I was doing everything in Perl. And I actually ended up writing this this script called renderer.rb, renderer.pl, and what you gave it on the command line was a function of x and y.
Oh, nice.
So basically, you could write x squared plus y squared less than 1, and well, not less than 1. X squared plus y squared. You could emit that. Of course, it doesn't exist. And yeah, you would have to do less than 1 and then render out some color of blah blah blah, otherwise black or whatever. And it was a Perl script, so you actually had to basically say black equals 0, and color is some function. You had to define it all right there on the command line.
Right.
But what my script would do is it would pick this entire thing up, wrap it in an eval block, basically. In Ruby terms, we would take this whole thing and create a lambda that accepts x and y and evals the entire command line that you wrote as a program, and then over whatever you basically say x is 640 and y is 480. It would then loop from 640 to 480 and evaluate. It would pass x and y to your entire program that you entered at the command line, and it would render your entire scene. And I very quickly had command lines that were like 600 characters long, and it was a full-blown Raytracer. I actually had, I was rendering spheres with cones next to them, and people were like, what are you using, like Pavre to generate stupid images for? And these were images for the test suite, and I'm like, no. Actually, I'm not. And yeah, what it would do, it wouldn't use ppm, but it used this is on Windows, and the BMP format, the bitmap format, is probably very similar to ppm in that there's a two-dimensional array of pixels and there's no compression.
Right.
So you just fart out this huge rectangle of color values and you're done. And actually, I take it back. It was probably a TIFF image back then, because you could spit out 32-bit, 24-bit color in a TIFF image, and there was no compression on those either. And so you just spat out this rectangle, and it would do all this rendering for you. And so that's kind of where the spirit of this Ruby thing came from, which is that. Once upon a time, I had written this Perl script that would let you give it an arbitrary mathematical function in terms of x and y, and that's all a Raytracer is, right? Given some x and y, trace out from the viewer's eye into the scene and figure out what that ray, trace out the path that ray would take, reflecting and bouncing off, and each time it hits a surface, calculate the angle at that surface and how much diffuse light there is and how much ambient and how much specular gradient there is to each light source in the scene, and that's all a Raytracer is. And so anyway,
we should probably say there too, for people that aren't familiar, in a Raytracer you work backwards and trace from the eye to the light source, because if you do it the other way, from the light source to the eye, it's way too much math for a computer to do.
Oh yeah, it's infinity math.
Right.
Like taking out, it's just impossible. It really is just impossible, because like to take a sphere and say what does this look like to the viewer it's a nightmare, right? I mean, it's what if there's something in front of the sphere? What if the entire sphere is behind a cube? We just wasted a whole lot of computational power, visualizing this sphere when it turns out that the eye can't even see it.
Right.
And the Raytracers sound really hard and complex. And when I was in college, they were hard and complex. They were presented as challenging math. And nowadays we almost take them for granted, because really all you're doing is, when you look at your monitor, if you look at the top left corner, you have to look up and left, and there's an angle from your eye going up and left to that top left pixel. And that's the Raytracer starts with that angle, and it just shoots a ray off into the scene and says, does this ray hit anything? Probably not if it's the top left corner and you've only got one or two objects in the scene. So okay, this image didn't hit anything. It went to the background. What color is the background? And we draw, in this case, we draw an underscore. And now we move on to the next pixel. What angle would the eye be looking at? Eventually you get to the center of the screen. What angle would the eye be looking at? Well, flat dead level right down the z-axis at this point. And what does it hit? Well, it hits the center of the sphere. And the sphere is indirectly lit in this scene, so we have to calculate these angles. And yeah, a Raytracer, that's exactly what it does. It traces, as you said, backwards from the eye into the scene. And And the crazy thing is that we've been raised to treat, a light source. We treat it as the source. It sources light. The light comes out of that source, hits something, and then bounces into our eye. But after you play with ray tracers for a while, you start thinking in terms of my eye is the source. My eye is the origin.
Right.
And if not the source, then certainly it is the destination, and we always start at the destination and work backwards.
Right.
Anyway, that's ray tracers in a tweet.
That's awesome. It's pretty cool stuff. I definitely want to play with it a little more and see if I can do a couple of simple things. Thanks for showing me how you did it.
You bet. This was a lot of fun.
It's pretty cool stuff.
Let's see if I can... There we go. Turn screen share back off, go back to camera, and I guess it's a good stopping point. So
yeah,
we'll stop the broadcast.